We'll now cover acid-base properties of ions and salts. This is one of the most important homework assignments that we will cover for the next test. Okay, homework 33 is going to be something very important. It's going to cover about 25% of the test, so this is something that you really have to concentrate on and understand, because we're going to use this concept when we get to neutralization reactions and we get a product. We're going to have to look at that species, if it's a salt, and decide if it's going to be acidic, basic, or neutral, and where we go on with the hydrolysis from there. Okay, so important concept in this particular homework set. One of the successes of the Bronsted-Lowry concept of acids and bases was in pointing out that some ions can act as acids or bases. Okay, so basically it's not just molecular species can be acidic or basic. Ions can also undergo hydrolysis and also add acidity or basicity to the pH of a solution. Let's look at sodium cyanide. Okay, sodium cyanide is a soluble salt, which means that it's going to ionize, and that ionic bond is going to break, and it's going to form sodium ions and cyanide ions. Okay, well, the sodium and the cyanide ions are capable of changing the acidity or basicity of the solution. Okay, the sodium ion, okay, basically, since it has a charge, positive charge, it can attract to the oxygen on water. And since water, the oxygen has a negative charge on it, it can attract to that oxygen. Okay, it can actually attract to that oxygen. Okay, so we have an attraction to that oxygen. When it attracts to that oxygen, what happens is it weakens the oxygen-hydrogen bond, and it produces H pluses. So in essence, a cation, depending on the size and the charge on it, could have an attraction for that oxygen and produce H pluses, or it may not have an attraction, and basically it could be neutral. Okay, so usually your cations are either neutral or add acidity to the actual solution. Cn minus, that's anion, the opposite effect's happening. Basically, since it's a negative charge, it can be attracted to the hydrogen on the water molecule. And the hydrogens tend to have a plus charge on them. So there's an attraction between that minus and that hydrogen plus. What happens here is we weaken the bond between the oxygen and hydrogen, and we produce OH minuses, which is adding basicity to the solution. So depending on what the anion is, it may have an attraction to the hydrogen or it may not. If it has an attraction, it will produce hydroxides. If it doesn't, then it will be adding neutral to the solution. In this particular case, I know that sodium will not be attracted to that oxygen, so it's not adding anything to the overall solution, but I do know that the Cn minus is adding some basicity to the solution. So we know that cations either add neutral acidity. In this case, sodium is adding neutral. And cyanide can add neutral or basic to the solution. And in this case, it's adding basic. So in essence, sodium cyanide is a basic soluble salt, which means it's going to have some basic pH in the solution. Now, I didn't tell you how I know that sodium is going to be neutral and cyanide is going to be basic. We'll talk about that later on in this section. Okay, so I'm going to be able to look, you should be able to look at a salt and look at the cation and look at the anion and make a decision to whether it's basic, acidic, or neutral. If we had a 0.1 molar solution of sodium cyanide, and that's not a very high concentration, okay, 0.1 molar solution, the pH of that salt would be 11.1, okay, and that basic pH is coming from that cyanide. That cyanide is able to undergo hydrolysis and produce hydroxide ions, which is given the higher pH of that solution. The sodium ion is unreactive with water, but the cyanide ion reacts, okay, to produce hydrogen cyanide and hydroxide, making it a basic solution. Since it undergoes hydrolysis, you basically will write your reaction. You take your cyanide ion, which is a base. Water in this case has to be the acid, so we use our Bronsted-Lowry theory, which means the base will accept the proton from the acid, so hydrogen will be donated to the cyanide. Okay, so that will produce HCN and OH minus. Okay, the water lost the hydrogen, so what's left is OH minus. Since it's producing OH minuses, this is what's causing the pH of the solution to increase. Okay, we're forming hydroxide ions, which is adding basicity to the solution. So from a Bronsted-Lowry point of view, the cyanide ions act as a base because it's accepting that proton from water. So even though this is an ion, it still can undergo hydrolysis. Everything we did before has been molecular substances, but ions can also undergo hydrolysis. You can also see that the hydroxide ion is a product, so what we expect to happen is that the solution will have a basic pH. This explains why your sodium cyanide solutions are basic, okay? Because of that OH minus, it's producing more OH minus during that hydrolysis process, so therefore the sodium cyanide is a basic salt. The reaction of the cyanide ion with water is what we refer to as the hydrolysis of cyanide. The hydrolysis of an ion is a reaction of an ion with water to produce the conjugate acid in a hydroxide ion, if we're talking about a base, okay, or the conjugate base in the hydronium ion if we're talking about an acid. So the anions, which can be neutral or basic, those anions can undergo hydrolysis and possibly make the conjugate acid and hydroxide ions. The cations are neutral or acidic. If they happen to be acidic, then they will make a conjugate base in the hydronium ion. So the hydroxide ion is adding the basicity to the bases, and the hydronium ion is adding the acidity to those cations. So you have your Cn minus undergoing hydrolysis. So going by your conjugate acid-base theory, your acid will donate the proton, which will form your HCN and OH minus. So therefore there's equilibrium here. We've got the double arrow. So therefore we will have some equilibrium constant. So you'd write your products over reactants, with water being 1 again because it's a liquid, and there'd be some K associated with it. Since we're talking about a base hydrolysis producing OH minus, then we're talking about a KB problem. So we can set up the ionization constant for this particular reaction. We write our products, which is the concentration of your hydrogen cyanide times the concentration of your hydroxide ion divided by your cyanide ion. Notice in the products, since we're dealing with this, we have an ion in the products, while all the previous problems have been molecular substances. It's all written exactly the same, and since we're talking about a base hydrolysis, it's going to be KB. It'd be a KB problem. Now, one thing I want to bring to your attention right now is that typically in the tables of ionization constants, they're all of molecular species. Now we're getting to the point that we're going to be using some ions, so you're going to have to do some conversions between your Ka, Kb before you work problems. What do I mean by that? Well, say you were saying you had sodium cyanide, and I wanted to know the pH of that solution. Well, we're saying that the cyanide undergoes hydrolysis, so what I need is the Kb of the cyanide ion. Well, most likely what you're going to be given in the problem is the conjugate acid of that, which would be the Ka of HCN. Okay? That's typically because it's a molecular species of it. I can't use the Ka, I got to use the Kb, so you're going to have to take that value of Ka and convert it into Kb and do the problem. Okay? So, in essence, after you do your salt, you do your hydrolysis, you know what's K it is, you might have to do a little bit of calculation to figure out what the K is to actually do the problem. Okay, something to watch out for, something common when you're dealing with salts. Most likely you're given the molecular species and you got to convert it to the ion. Okay, the conjugate, if you got the conjugate base, then you need the conjugate acid species to be able to do conversion. I'll tell you more about how to do that calculation later on in the next homework set. As I noted, basically we're saying here you would need the Kb of the Cn minus, but probably will be given the Ka of the HCN because the ionization tables tend to be a molecular species, and you're going to need to convert that to get to the K that you need to do your calculations. I'm giving you a warning of that now. We'll eventually show you how to do it later on in problems. Here's an example of a cation that undergoes hydrolysis. Okay, now we're talking about ammonia chloride. Okay, this once again is a soluble salt. Soluble salt is going to break on an ionic bond and form ammonia ions and chloride ions. That ammonia ion could be either neutral or it could add some acidity to the solution. Well, that's a very big ion, so that will have some attraction. I mean, that ion will have some attraction for the oxygen, so it's going to produce some H pluses. So I know that that's going to add some acidity to the solution. Okay, the chloride ion I know is not going to be attracted to that hydrogen, so therefore it's not going to add any basicity to the solution. So I know that's neutral. Okay, so what happens is this happens to be an acidic salt. Once again, I haven't told you how to look at ammonia or look at chloride to decide that. I will tell you that more later on in this particular homework set. Okay, so what we're saying here is that I have an acidic salt. Once you know you have one species undergoing hydrolysis, then you have to do the hydrolysis. So once I know that this is adding some acidity to it, I have to do the hydrolysis of that particular reaction. I'm not going to worry about the neutral one because it's neutral, it has no effect on the pH. So how do you do the hydrolysis? Well, you write your species, which we said is an acid, which basically means water is the base. So my acid will donate the proton, which now gives me hydronium ion and ammonia. Anytime I'm talking about an acid hydrolysis, I should be forming hydronium ion. If I'm talking about a base hydrolysis, I should be forming hydroxides. Since this is an equilibrium, once again, I can set up products over reactants. So I have my ammonia times my hydronium ion divided by my ammonia ion. And since this is an acid hydrolysis, this is going to be a Ka. This is going to be a Ka ionization constant. Okay? Talking about a base, it should be Kb. Once again, how would this work in a problem? Well, if we were talking about ammonia chloride, now I'm looking for the pH of this solution. Most likely, okay, I'm going to need the Ka of ammonia ion, okay, because I'm looking at the Ka of that reaction the way it's written. Most likely I'll be given the conjugate base, which would mean I'll probably be given Kb of ammonia. I can't use that value. I'm going to have to take that value, that Kb, and convert it into Ka. As I said, I'll show you how to do that on the next homework set. A 0.1 molar solution of ammonia chloride would have a pH of about 5.1, so therefore it's pretty acidic. So the question comes up, how do you predict whether a particular salt will be acidic, basic, or neutral and undergo hydrolysis? How did I know that sodium I didn't have to worry about, chlorine I didn't have to worry about? I had to worry about ammonia and I had to worry about the cyanide. How did I know that? How did I make those decisions? The Bronsted-Lowry concept illustrates the inverse relationship in the strengths of conjugate acid-base pairs, meaning the stronger conjugate acid, the weaker the conjugate base. Okay, we discussed this earlier in other homework sets. Consequently, then, the anions of your weak acids are good proton acceptors. Anions of the weak acids want to accept protons, which basically means anions of the weak acids are basic. Okay, anions of your weak acids are basic. So that would mean your anions of your strong acids are not. They tend to be neutral. Okay, so the anions of your strong acids tend to be neutral. So on the other hand, the anions of the strong acids, that are good proton donors, have virtually no basic character. That is, they do not undergo hydrolysis. Therefore, the conjugate base of the strong acids do not undergo hydrolysis and are neutral. Now, I kind of already explained this once before too, with chlorine being my example, but let's look at HCl and its conjugate base Cl-. I got HCl, which is a strong acid, so it breaks up into Cl- and H3O+. since Cl minus is a conjugate base, it seems reasonable then that we should be able to undergo hydrolysis with that species, okay, with water, with Cl minus being the base and water being the acid, which means my proton will be donated, which will form HCl and OH minus. Well, in that process, I made HCl. What is HCl? Well, HCl is a strong acid. What happens to a strong acid? Breaks up 100%. So it forms Cl minus and H3O plus. Well, you notice I have 1 mole of HO minus, hydroxide ion, and I have 1 mole of H3O plus. Well, if I have one of each, what happens between those two species? They neutralize each other, which basically means form water, so they cancel out. Okay? Which means I'm back to where I was originally. I have Cl minus, which is where I was before. So in essence, the Cl minus does not want to undergo any appreciable hydrolysis. So bottom line, okay, chlorine plus water is basically no reaction. So when I see chlorine in my reaction, I cross it off and say that's neutral. Okay, it's neutral and I do not have to worry about it. Basically, those conjugate bases of those strong acids are the ones that are going to be neutral. Any other anion, I'm going to have to worry about basicity in my reaction. Okay, what about cations? Okay, well, small, highly charged cations have an attraction for the oxygen on the water, causing more production of hydronium, while large, low-charged cations do not. Okay, we can look at this in two different ways. One, we can look at it as size. If I have a species that's this size with a positive charge compared to something this large with a positive charge, both of them are attracting to that oxygen on the water molecule. Okay? Well, which one's going to get pulled more? Which one is the oxygen going to be attracted more to, the smaller species or the larger one? The smaller one, it's closer, so that positive is closer to the negative of the oxygen, so it's going to pull more on it, therefore weaken the bond and produce H pluses. So the smaller species is one that's going to worry about this more. Okay, the smaller species is going to happen this more and produce more H pluses. Okay, now what about charge? Look at something with a 3 plus versus something with a 1 plus. Once again, let's compare that to the water. Which one of those is going to be attracted more to the oxygen? The one with the 3 plus or the one with the 1 plus? Well, the higher the charge, the more pull it's going to have. So once again, this is going to pull on that oxygen more, weaken the bond, and cause H plus to come off. So once again, the higher charge one is going to cause that to happen. If you look at the periodic table, where do we have our largest ions? That would be on the far left bottom, that whole area there, because your trend for metal for radius goes down and to the left. This is where the larger species are located. Okay. Now, where are the lower charges? Once again, same area. Okay, this is where our lower charges are as well, which is also where the lower charges are. Okay, they're also in the same area. What we have in common between the two is over on that side we have the larger species with the lower charges. That's also happen to be the same cations that are involved with the strong bases. Okay, so in essence we can look at the strong base cations and say they're the ones that are going to be neutral. Okay, the cations of those strong bases are the ones that are going to have neutral. Any other cations are going to have some effect on the pH of the solution. So low charge large ions are group 1 and 2 metals. Okay, low charge large ions are the group 1 and group 2 metals. In other words, the cations of the strong bases. They do not undergo hydrolysis. They're pretty much neutral. So this is why when I looked at sodium, I'm saying sodium plus water, we're saying this is such a large species with a low charge that it basically does not want to undergo any hydrolysis. There's no reaction. So therefore I can eliminate the sodium while I'm looking at the species. Summary. If a cation is that of the strong bases, meaning sodium, potassium, lithium, strontium, barium, and calcium, if it's any one of these ions, which happens to be the cations of those strong bases, it's neutral. Okay? Otherwise, any other cation, I have acidic hydrolysis. Okay, all the rest of them, I have acidic hydrolysis. If the anion in a monoprotic strong acid, meaning those anions of the monoprotic strong acids, nitrate, chloride, bromide, iodide, perchloric, if it's any one of those, it's neutral. Okay, any other anion, we got basic hydrolysis to deal with. Okay, so you learn these cations, you learn these anions, those are all neutral. Anything else for the cation, you got to deal with acidic hydrolysis. For the anion, you got to deal with basic hydrolysis. As I said, this is very important, something you got to know. Now, if you can memorize them or learn them as the cations of the strong bases or the anions of the monoprotic strong acids. So, what I need to do is look at a salt, which could be acidic, basic, or neutral. And I got to look at the cation and I got to look at the anion and decide overall what's going to happen. Okay, so if the cation, I'm looking at there to decide if it's acidic or neutral. If it's the cations of the strong bases, okay, if it's a cation of a strong base, then it's neutral. Otherwise, that cation, it contributes some acidity, and I got some hydrolysis to deal with. The anion, it's either basic or neutral. Okay, the anions of your monoprotic strong acids are neutral. So if it's any one of those, it's neutral. Otherwise, it contributes basicity. Or another way of looking at it is looking at the actual atoms. Okay, the elements involved, the ions involved. Okay, you got sodium, potassium, lithium, calcium, strontium, and barium. Any one of these, we know it's neutral for the cation aspect of it. Anything else, we got to add acidity. Chloride, bromide, iodide, nitrate, perchlorate. Any one of these, okay, I know it's neutral. Okay, any of the rest of the anions, it's adding basicity to it. So I'm just looking at the cation and anion and looking at it as a whole to see what's going to happen. So to predict the acidity or basicity of a salt, you must examine the acidity or basicity of the ions composing the salt. So depending on two components, the cation and the anion, the overall salt will be acidic, basic, or neutral. So if I have a cation and it's one of those ones we memorized as neutral, and I have the anion and it is one of the ones we memorized as neutral, then the whole salt has to be neutral. Okay, the whole salt will be neutral. Whole salt is neutral. Now what if I have a component, my cation is acidic, it's not one of those ones I memorized as neutral, and my anion is one of the ones I memorized as neutral, then what happens to the overall salt? It's acidic. Okay, the overall salt will be acidic. This is an example like we just did with ammonia chloride. Okay, ammonia was one of those ones we didn't memorize as neutral. Chloride was one of the ones we memorized as neutral. This is adding acidity, this is adding neutral, so the whole salt is acidic. Okay, what about if I have a cation that is one of the ones I memorized, then it's neutral. What if the anion is not one of the ones I memorized, then it's contributing basic? Well, then the whole salt is basic. Example, one we just talked about a few minutes ago, sodium cyanide. Okay, sodium is one of the ones we memorized as neutral. Okay, so that's neutral. Cyanide is not one of the ones we memorized as being neutral, therefore it's adding a base to it, so the whole thing is a basic salt. Now what happens if you answer the question and the cation isn't one of the ones that's neutral, so it's adding acidity. The anion is not one of the ones you memorize as neutral, it's adding basicity, so you had both of them. Then how are you going to decide? Well, you got acid-base neutralization going on, competition. So what's going to depend on it is the larger Ka or Kb. The larger your Ka, the more it ionizes and forms hydronium ions as compared to the Kb. Okay, so the one with the larger K is going to win, because if it has a larger K, that means it's ionizing more, which means if it's Ka, it has more hydronium. If it's Kb, it means it has more hydroxide. So if I got more hydronium, it's acidic salt. If it has more hydroxide, it's a basic salt. So it's competition. Now, this is not one that we're going to run into in this class. Everything we're going to do is going to be one or the other. Okay, it's either going to be neutral, acidic neutral, or neutral base. But I do want you to realize that it is possible that you have acidic in base, and what's going to dictate that would be the Ka or Kb. So let's go over the problems that we just did, and let's see if we can if we can make the same conclusion that I told you earlier about these salts. Ammonia chloride, soluble salt, breaks up at that ionic bond. It forms ammonia ions and chloride ions. So now you got to look at the cation and the anion, decide about the overall salt. Is ammonia one of those cations you memorized as being neutral? No, it's not one of the ones on the list. So therefore, it's going to add what to the solution? Acidity. Okay. Is chloride one of those ones we memorized as being neutral? The answer is yes. It's one of those conjugate bases of strong acids, so it's neutral. So what effect is this whole salt going to be? If I have an acidic cation and a neutral anion, the whole salt's going to be what? Acidic. Okay, as we discussed earlier. Now, where will we go from here to actually work the problem? Well, from this point, neutral's not affecting the pH. Neutral's not affecting the pH, so I ain't worried about that. But this is now affecting it. So from here, if I wanted to calculate the pH of the solution, I would have to do my hydrolysis of that ion, which would be my ammonia ion plus my water. Gives me my ammonia plus hydronium ion. Since it's an acid, it should be giving me some hydronium ions. And then I would work this just like products over reactants, and this would be a Ka problem. Okay, because I'm talking about the Ka of this reaction. Let's get this one. We talked about this one earlier. You got sodium cyanide, soluble salt. It's going to break up into sodium and cyanide. Is sodium ion one of those ones we memorized as being neutral for the cations? Yes, so therefore it's neutral. Is cyanide one of the ones that we memorized as being one of the neutral species? The answer is no. That's not one of the conjugate bases of the of the strong acids. Therefore, it's adding what to the solution? Basicity. So if I got something added neutral and something added basicity, what's my overall salt? Basic salt, which we discussed earlier. Now, where would I go from here if I was actually trying to calculate the pH of the solution? Well, though I'm not going to worry about the sodium because it's neutral, I will worry about the cyanide because it's adding basicity. So then I would have to do my hydrolysis, which would be Cn minus plus water. Gives me 8Cn plus OH minus. And since we're talking about a base hydrolysis, my K would be what? A Kb. Now here's one we haven't covered, so this is new. Let's see if we can do it. Got potassium acetate, which is a salt. Okay, remember a salt is a metal, non-metal, a metal polyatomic ion combination that doesn't involve hydroxide, oxide, or hydrogen as the anion. Okay, so now I have this break up into my cation, which is my potassium plus, and my acetate, which is my anion. So I look at the potassium. Is that one of the cations I memorized as neutral? And your answer is yes, so therefore it's neutral. Is acetate one of those ions I memorized as being neutral? And the answer is no. So that means it adds what to the solution? Basicity. Okay, so what's my overall salt then? I got a neutral and a base, therefore the overall salt will be basic salt. pH will be less than 7. If I wanted to calculate the pH, wouldn't worry about the potassium, but I would worry about the acetate. So then I'll have my acetate plus water. Okay, my acetate's my base, so it's going to accept the proton, which then gives me acetic acid plus my OH minus. And what would the equilibrium look like? It'd be Kb, which would be, if I want to write the whole thing, it'd be my concentration of my acetic acid times my concentration of my OH minus divided by my concentration of my acetate. Okay? And then work the problem from there. Now, most likely, though, I won't be given the Kb of the acetate. I most likely will be given the Ka of my acetic acid. Okay, so I'm going to have to convert this. I'm going to have to convert this from Ka to Kb to work my problem. Now, I haven't shown you how to do that yet, but we will show you that on the next homework set. So let's look at some salts and see if we can look at them and decide what kind of salts they are. I got aluminum chloride. Okay. Is aluminum one of those metals that we memorized as being neutral? And the answer is no. So what? It's adding some acidity. Is chloride one of those anions that we memorize as neutral? The answer is yes. So it's neutral. So my whole salt in this case would be an acidic salt. So if I wanted to calculate the pH, I would take that aluminum 3+ and do my hydrolysis and do a Ka problem. Let's look at zinc nitrate. Is zinc one of those ones we memorize as being neutral? And the answer is no. So therefore it's adding acidity. Is nitrate one of those ones we memorize as being neutral? Yes, it is one of those ones. So therefore it's neutral. So the overall salt would be an acidic salt again. Once again, if I wanted to calculate the pH, I'd take that zinc 2+, do my hydrolysis, Ka of that zinc 2+, and work on from there. Let's look at potassium perchlorate. Okay, is potassium one of the ones we memorize as neutral? And the answer is yes, so that's neutral. Is perchlorate one of the ones we memorize as neutral? The answer is yes, it's neutral. Therefore, what is the overall salt? Neutral. So the pH of this salt, the potassium perchlorate, should be close to 7 pH. Should be no acidity or basicity to it coming from these ions. So it should be pretty close to a neutral solution. Look at sodium phosphate. Is sodium one of the ones we memorized as neutral? Yes. Is phosphate one of the ones we memorized as neutral? No. So therefore, what's it doing? Adding some base to the solution. Therefore, what kind of salt is this? It's a basic salt. So I would take my PO43-, do its ionization, okay, my hydrolysis, and then do a Kb problem. Lithium fluoride. Is lithium one of the ones we memorize as neutral? Yes. Is fluoride one of the ones we memorize as neutral? No. Therefore, what is it? Add basicity to it. So therefore, my overall salt is a basic salt. I would take the F-, do the hydrolysis, do an Kb problem. Let's look at ammonia fluoride. Is ammonia one of the ones we memorized as neutral? And the answer is no. So what does it add to the solution? Acidity. Okay. Is fluoride one of the ones we memorize as neutral? And the answer is no. So what does it add? Basicity. So this is a case where I got both components adding something to the solution. So how am I going to dictate? What's going to dictate what's going to win this battle? Which one's going to contribute more? Which one's going to be given more hydronium or more hydroxide? Well, we got to look at the Ka and Kb. So you look at it, we got 5.6 times 10 to the minus 10 versus 1.4 times 10 to the minus 11. Which one's larger? Well, the Ka is larger. Since the Ka is larger, that means it's ionizing more, which means it's producing more hydronium. Okay? Than the OH minus, therefore, it's going to be more acidic. What about ammonia hypochlorous? Well, once again, ammonia is not one we memorize, so it's adding some acidity. Hypochlorous is not one of the ones we memorize, so it's adding basicity. So once again, I got to look at the Ka, Kb. If you look at it, I'm comparing 10 to the minus 10th times 10 to the minus 7th. So my Kb is larger. That means it's going to ionize more, which means it's going to produce more hydroxide in comparison to the hydronium. So therefore, what is this salt going to end up being? A basic salt. What about ammonia acetate? Well, ammonia contributing acidity, acetate basicity. The Ka is 5.6 times 10 to the minus 10th. Kb is 5.6 times 10 to the minus 10th. So what do you think's happening here? Yes, they're neutralizing each other out, so it ends up just being a neutral salt. Now, this is the only example I know of that the Ka and Kb are the same. Now, as I said before, we're not going to worry about acid base. I just want you to realize it's available and how to do it, but that's not what we're going to be dealing with. Everything we're going to be dealing with is going to be either neutral, one of them acidic, or one of them basic. And then we go on from there with our hydrolysis. Homework 33, as I mentioned earlier, this is a very important homework, okay? Extremely important homework set, okay? Very important. You need to be able to look at species, decide if it's an acid or base, because later on when we do neutralization reactions, you're going to come up with a product. You got to look at that product and say, is that something I got to worry about? Is that just a neutral salt, or is that an acidic salt, or is that a basic salt before I can go on to my hydrolysis? Everything we're doing right now is leading you to doing the neutralization reactions. We basically building as we go on. We already learned the bottom, and we keep putting a step above, and above until we get to what our ultimate goal is a reaction between two species and figuring out what the pH of the solution is. And this homework set is going to be crucial for that determination of what do I do next.